This problem's obviously a XY problem, really Y only, but it involves this pulley. And so this is an example of where you can take a problem that's relatively simple, but throw a little twist in it by including something that you learned earlier, the absolute relative motion using pulleys. And remember, in those problems, you get the length of the rope, and the rope has to be constant. Well, this is a little confusing because the rope's being wound up into that winch. And so what I'm going to do is I'm going to just tie orange ribbon right over here. Okay, so to mark that. And I'm going to call that point D. And what we're going to do is we're going to keep track of the length of the rope from point D all the way back to the underside of the beam. And so let's call the distance from the datum, we'll take as the bottom of the beam. So we'll call the distance from the bottom of beam to pulley as SC. And we'll call the distance from the bottom of the beam to the ribbon SD. Okay, so the total length of the rope from the ribbon back up to the beam is L is SC minus SD, okay, plus SC plus the little bits that are left over. You take the derivative of both sides, and the length is constant. SC dot minus SD dot plus SC dot plus 0. So you get SD equals 2SC dot, and similarly the accelerations SD double dot equals 2SC double dot. So D is going up at 3 meters per second squared, and since we took down is positive, so minus 3 meters per second squared equals 2 SC double dot, which means the box or the crate is accelerating at 1.5 meters per second squared up, because I, for some reason, took down as positive. Okay, so once we've got that out of the way, let's draw a free body diagram. So we're going to need the force of the ropes on the beam to get the reactions. So it makes sense to me that the free body diagram is going to have to cut through both of the ropes and include the box. So there's my closed loop. And again, the rule for drawing free body diagrams, just draw what's in the box. So here we go. We've got the box in there, this little pulley, and the 2 bits of rope coming up. That's what's in the box. Then draw the forces that are in your loop. And so the only thing in the loop is the weight of the box. So I'm going to just say mass of C for crate, I guess, times G. That's the weight. And then you put in the forces you cut through with the loop, that red loop there. So we cut through the rope twice. The tension is the same in the rope on both ends, so I'm just going to write T. Okay, so that's the free body diagram, and it equals the mass times acceleration. And so we went through all this pulley and rope stuff so that we could get the acceleration, which is going up, MC at 1.5 meters per second squared. Okay, so it's relatively straightforward. There's only one direction. We'll say sum Fy equals Ma y. So we got, and I'll take up as positive this time, 2t going up minus mc times g equals 1.5 times mc. So 2t equals mc times 1.5 plus g. And finally, the tension is half of that. Let's plug in some numbers. The crate is 200 kilograms. And 1.5 plus 9.81 all divided by 2. And so that equals 1131 newtons, or 1.131 kilonewtons. So now that we know the tension, we can draw the free body diagram of the beam. And so here's the beam. There's the reactions at A, reaction at B. Here's that little winch on here that had the rope like this. And if you look at the free body diagram I drew up above, let me scroll up, cut through the two ropes there. That will have tension, which we know is 1.131 kilonewtons. And we also have the weight of the beam, which happens to be right above that second rope there. And earlier I said it was 30 kilograms, I believe, but that was wrong. I read the problem more carefully. The mass is 30 kilograms per meter, and so it's 6 meters long. So that's 180 kilograms. That's the mass, and multiply it by g to get the weight. And that will all equal 0 because the beam is not moving, only the block, which we solved for earlier. So what I'm going to do is I'm going to plug in the numbers and redraw that a little nicer, and then we can continue. Okay, so I've drawn the free body diagram a little nicer and to scale, and so here it is. And so now we just need to solve this like a regular statics problem, because acceleration is 0. So I'm going to get the reaction at B. So to do that, I'm going to take moments about A, and it's equal to 0. This is a statics problem now because the beam's not moving. And I'm going to take counterclockwise positive. So I've got all the dimensions in there. So now this is just like statics. So I'm going to take moments about A. Minus 1.131 times 2.5 counterclockwise. Minus 1.131 times 3 counterclockwise. Minus 1.766 kilonewtons. That's the weight, total weight of the beam. Also times 3. And finally, plus the reaction at B. That reaction is going counterclockwise around A times 6. All equals 0. And that gives us that RB equals 1.92 kilonewtons up. I'm going to sum forces in the x direction. That's easy. Sum forces in the x direction equals 0. RAX equals 0. And then finally, sum forces in the y direction equals 0. And again, this time up is positive. I got RAY minus 1.131 minus 1.131 minus 1.766. Those are all the downward forces. And then reaction B we got as 1.92 up. All equals 0. And that gives us finally that RAY equals 2.11 kilonewtons going up. So there you go.